Okay, so good morning.
Good morning, sir.
Good morning too. All right. So let's just have a few minutes to to talk about maybe you have a question regarding with the module one. So let's talk about last meeting. So anyone who has a question so far regarding with the module, with the quiz, with the case study? Or any clarification so far? Okay, so I guess none. So if you guys don't have a question, so just give me thumbs up, just to let me know that everything is okay. Okay, great. So it's like 80 to 90% responded. I don't know who the others. Anyway, so I hope you guys have already checked the, some of the things that you can find here on the week two module two. So as usual, you have the overview right here. So again, I will leave the reading part to you guys. And then here's the PDF itself for the module two, which is namely chapter two. And then I have prepared here four basic exercises, of course, just to help you understand more what is this chapter two all about or module two all about. And then after our discussion, so yeah, you're going to have a quiz. Well, actually, you can take this one now since this is already available. But of course, before taking that one, make sure to you already know everything, okay, regarding with this chapter two. And then of course you're going to have another case study, which is namely case study number two. Okay, so those three activities will be due on September 13th. So you guys have exactly 1 week, okay, to finish, okay, all of those activities. So are you guys ready now to talk about chapter two?
Yes, sir.
Okay, great. So this will only be a short meeting, so maybe part one and part two only. So I hope we can finish it one faster than that, so that we can save more time, and then you can use the remaining time for the thing that you might want to uh, use it or to finish something. But anyway, so in this chapter, we're going to talk about diode circuit analysis and its applications. Okay, so to make it simple, I have this uh, you know, uh, for this one namings, we're in ideal diode, second approximation, and then third approximation. So I will explain this one in an example way. Okay, so there is no definition or there's no meaning. So ideal diode is like the first approximation. Okay, so ideal diode or first approximation, so they are just the same. And then second approximation is your second approximation, to be exact. Okay, but to make it more understandable, when say second approximation, we are now adding more information. Okay, so we could say that this one now is a little bit more accurate than the first approximation. Okay, so we could say that the first approximation is like your first judgment, and then second approximation is like your second or third judgment to that person. Since like, maybe in first judgment, you just saw that person. But in second judgment, you were able to talk to him. You were able to, see more about, or yeah, see more about his characteristics, his face, maybe his PCQ or anything, okay, everything that might clear up uh, the information about that person. And then the third one is like the complete examination on that person. So you know him or her already completely. Okay. So in other words, this is our first judgment, and then this is how we already completely know that person is. Okay. Well, anyway, so let's have another example. So what are those approximations? So if someone asks you like, how old are you? Okay, so you could just say I'm 21 years old. Okay, so this is the general answer, okay, or the normal answer. But if you want to be more precise or to be more, to have more, to add more information with it, so you can answer maybe the second approximation. So you could say I'm 21 years old and 9 months old. Okay, so you're now adding, specifically the months. And then if you want a super complete answer, okay, so you could use a third approximation wherein I'm 21 years old and 9 months and 3 days and 30 minutes and 40 years old, something like that. Okay, so in other words, this is the general answer. Okay, so this is what we are, we are going to do as always, since this is less hectic, rather than considering more information and then more and more specific information. Okay, so I hope you guys have already an idea, okay, what are those approximation is. So again, in other words, first approximation is the general, and then third approximation is the complete, or more information on it. Well, anyway, let's have an example. So again, ideal diode or first approximation are just the same. So any of those two. So again, just a recap. So when we see forward bias, it works like closed switch, meaning there is a current that is flowing on that circuit. And when we see reverse bias, it's like an open switch. So there is no current that is flowing on that circuit. So here are the characteristics that you guys need to memorize. So in ideal diode, so it does not have a threshold voltage. Second, it doesn't have a resistance at all. Third, does not have a breakdown voltage. So what is this threshold voltage? So remember what I mentioned last meeting, that a diode always consumes a certain amount of voltage. So for silicon, it consumes 0.7, and then for germanium, it consumes 0.3. So I just can't remember if I said 0.4 last meeting, but if ever that's the one that I said, so I'm reclaiming it. So it's not actually 0.4, but it's 0.3 volts. Okay, so we call that one the threshold voltage of that specific diode. So in ideal diode, we don't consider the threshold voltage. Okay, so if it's silicon and if it's a forward bias, then it's closed switch. Okay, and if it's germanium, it's still closed switch. So they are just the same in ideal diode. Okay, and then second, we do not have a resistance at all. So what is this resistance? So to make it simple, in a circuit, okay, so we have resistors, right, to resist the flow of voltage or the flow of current. So a wire also has a very minimum, not minimum, very small, a very small resistance. Could be 0.005, 0.001, 0.0, or yeah, we cannot even notice that one, but it has a very uh, small resistance on that one, on that wire. So the same with the diode. Okay, it also has a resistance. Okay, so it's not just a component that work like a closed switch or work like an open switch. So if it's working like in a closed switch, it also has a resistance in it. Like for example, it's 0.05, 0.08. So mostly the resistance on that diode is less than 1 ohm. Okay, so it could be 0.5, 0.8, 0.9. Okay, so yeah, but sometimes the resistance is above 1 ohm. Okay, so it could be 1.5, 1.2, 1.3. Okay, and then lastly, it doesn't have a breakdown voltage. Okay, so this breakdown voltage only works in reverse bias, wherein yes, in reverse bias, it works like an open switch, like it doesn't permit any current. But if you have a like super high voltage source, then there is a chance that it will meet this breakdown voltage, wherein the flow of current now will flow on that circuit. Okay, so it doesn't work now like an open switch anymore, but it works now like a closed switch. Okay, So we'll talk about this breakdown voltage soon. Okay, but for now we don't have example for this one. So yeah, here's the graph for the ideal diode. So if you're going to apply a voltage, so of course you have an increase of current. Okay, so the left side we have the reverse bias wherein we have the negative voltage, and then on the right side we have the positive voltage. Okay, so it works completely as an insulator if it's reverse bias, and then it works as a conductor if it's in a forward bias. So this approximation is mostly the one that's being used in real life. So okay, mali pala. It is not used, my bad. Okay, so it is not used for real life situations, but just as general approximations when preciseness isn't needed. But well, I think this is what we always do. Okay, we always go with approximations unless we really need the super precise answer or super precise information. Okay, so yeah, that's it for the first approximation. So the second one is, of course, the second approximation, wherein here are the characteristics that you guys need to memorize or need to be familiar with. So you need voltage to turn on. So you now need the threshold voltage, wherein if it's a silicon, then you have to deduct the 0.7 volts now. Okay, the same with the germanium, but it only consumes 0.3 volts. Okay, and then the rest are the same. Okay, so this one also ignores the bulk resistance or the resistance. So yeah, by the way, the one that being mentioned here, that that is the resistance, we actually call that one bulk resistance in diode. Okay, so resistance is a common term when it comes to resistors, but in diode we call that one bulk resistance. Okay, so specifically the resistance or the resistors that the diode has. Okay, so it is approximate resistance across the terminals of the diode when a forward voltage and current are applied across the diode. So it is the resistance of the P and N materials of the P and N junction of the diode. So its value is dependent on the doping level and the size of the P and N materials. So maybe if you have a super big diode, then maybe uh, the bulk resistance is above 1 ohm. Okay, but if it's just a normal diode, mostly the value of that one is less than 1 ohm. Okay, so this is the only additional in second approximation. You now need to consider the voltage threshold of that diode. Okay, and then the last one, to make it simple, you need to consider everything. Okay, so you need the voltage threshold, which is the same, and then you now need to account the bulk resistance. However, it says here that if the bulk resistance is less than 1 ohm, it can be ignored. Okay, so this is the major rule when it comes to resistance or bulk resistance in diode. So if it's less than 1 ohm, you can just simply remove that one or ignore that one. Okay, but if it's 1 ohm and above, then you have to include that one on the entirety of your circuit. Okay. So by the way, this is the graph for the second approximation. So as you guys can see, you have already applied a certain voltage right here, but your current is just, still not flowing, okay, or it still doesn't permit the current. That's because you have to consume the 0.7 volts first, okay, before it will have a flow of current. So in other words, you have to call this one, how do you say pakainin? Okay, so you have to feed, you have to feed your diode first an amount of a certain amount of voltage, like if it's silicon 0.7 volts, and if it's germanium, then 0.3 volts, before it can fully permit a current on that specific diode. Okay, so if you don't have enough voltage source, then you won't be able to pass through this diode. Okay, because it eats up a certain amount of voltage. And this is the graph for the third approximation. So before it's just a straight line, but since we know considering the bulk resistance, so it is now a slight, okay, like maybe a 95-degree or 90-degree, okay, rising of our current, since it is now resisting some of the current due to this bulk resistance. Okay, well, if this is less than 1 ohm, then you will have the same flow of current. But since we're seeing something like this, then that only means that we have a 1 ohm and above of resistance in third approximation, okay, or in this graph. So the complete drawing or icon for the die that has a bulk resistance is something like this. Okay, so we have the resistance itself, which is called the bulk resistance, and then the diode itself. But in real life, okay, you will only see the picture of the diode, okay, or just the diode, okay. So it's just that it is just showing here that this one has a bulk resistance, but in reality it actually has a bulk resistance, but mostly maybe it's less than 1 ohm, so that's why we can just ignore it. But in here, yeah, it's just to represent that we have a bulk resistance in this diode, okay, which is mostly maybe 1 ohm and above. Okay, so let's have an example for you to be able to appreciate more what are those first, second, and then third approximation. So calculate the total current, total resistance, and then the power across on each component using the first approximation, second, and then third approximation. So in other words, we're going to have 3 separate solutions. So for the first approximation, we have to compute everything. So the same in second, and then for the third one. Okay. So by the way, do you guys have a question so far up to this point before we start with the example number 1? Question or clarification?
No, sir.
Okay, great. Okay, so in this circuit, we just have a super simple circuit. We have a series circuit. So we have a voltage source of 8 volts. We have an 100 ohm of our resistance. And then we have the diode itself, which has a bulk resistance of 0.75 ohm. So in here, we already know that we're going to neglect this one, or we are going to ignore this one since this one is less than 1 ohm. Okay, so in other words, we just have a silicon diode which has a threshold voltage of 0.7 volts. So mostly, okay, in other circuits, we don't usually include the threshold voltage because it's already common sense that if it's a silicon, then it will consume a 0.7 voltage. Okay, so it will never change. That is a constant value. That is the default value or the permanent value of the silicon. So there is no way that this will become 0.6, 0.5, 0.8, or even 1 volt. Okay, so it is always 0.7 volts for the silicon diode. Okay, well, anyway, so here are the computations. So you can just simply use the Ohm's law to solve everything. So we have the total current. So I is equal to V divided by R. So V or voltage source is 8. And then the total resistance is 100. Okay. And then take note in the first approximation, even though we have a threshold voltage, we have to neglect that one. Okay. Since we don't consider the threshold voltage in ideal diode or first approximation. So the same with the bulk resistance, even though it's 1 ohm and above, so we don't consider that one, okay, in the first approximation. Okay, so for the third one, so this one only works in a reverse bias, okay. But if you guys are going to take a look on the first example, this one is complete working as a forward bias. So positive is connected to the positive, and then negative is connected to the negative part of your diode, okay. So in here, we have 0.08 for your total current. And then for the R total, of course, it's just 100 ohms. Okay. And then for the voltage across R1, we have uh, we have IR1 times R1. Okay. So we have 0.08 for the current and then 100 for the resistance of the R1. So you'll get 8 volts exactly. Okay. But without this formula, you can just just take a look on the circuit itself, because this one is in series connection. So of course the voltage that will blow on this diode is 8 volts. Okay. So no other voltage that will flow in here. And then for the power across R1, just use the P is equal to I times P. So I1 times VR1, so 0.08 times 8, we'll get 0.64 watts. And then for the power across RB, since this one is, or in ideal diode, we don't consider the bulk resistance. So that is the reason why we have 0 right here for the VRB. Okay, so any number that is multiplied to 0 will be 0. And then for the power across diode, so you're still in first approximation, so we don't consider the threshold voltage. So in other words, this diode is just like a closed switch only. So it's just like a wire. Okay, so we have a 0 threshold voltage. So any number that is multiplied to 0 will be 0. And then for the last one, we have the power across on your voltage source. So 0.08 times 8 is equal to 0.64 watts. Okay. So I will give you guys 30 seconds to 1 minute to recheck everything. And then just give me thumbs up once everything is clear to you guys, or if you don't have a question. Okay, so it's like there were 6 out of 22, 7 out of 22, 7, 8, 9. Okay, so what about the others? Okay, great. So it seems that most of you were able to get this one. Okay, so if you guys have a question, so just let me know. Okay, so that's it for the first approximation. Okay, so while we are at here, so let's recall what is the characteristics, or what are the things that we need to consider in second approximation. So in here, we now need to consider the voltage threshold of your diode. So if it's silicon, then you have to deduct 0.7, and if it's germanium, then you have to deduct 0.3. So in other words, all we need to do is deduct the 0.7 on our total voltage, and then of course we now have a different current. Okay, but for the R total, it's still the same, since in second approximation we don't consider the bulk resistance. Okay, so this will change, this will change, this will change, and this will change. Okay, but for the RB right here, this will still remain. Okay, though the value of current will change, but this one is still 0, since we don't consider the bulk resistance in second approximation. So as you guys can see, everything is will change. Okay, so there were only 1 or 2 that retains, but most of your answers will change in second approximation. Okay, so here is the solution for the second approximation. So we have 8 minus 0.7. Okay, and then we now have a current of 0.073. So the R total is still the same, but we now have a different voltage across R1. We now only have 7.3. Well, of course, 8 minus 0.7 is 7.3. And then we now have a different power across R1. The power across RB is still the same. And then the power across diode is now also different. So the same with the power across VS. Okay. And here's one way to check if your power, okay, your answer individual power across your components are correct. So you can use this formula. So P total is equal to PR1 plus PRB plus P diode. Okay. So again, I would like you guys to verify everything, so you can use your calculator and then please check whether my answers are correct or no. So I'll give you guys 30 seconds to 1 minute. Okay, so there is no one. Give me thumbs up. Okay. So 1, 2, 3, 4, 5, 6. So if you have a question, so ask it now. So the sooner, the better. Okay, so I have a question. So what if this one is the other way around? So we have a connection of reverse bias. Okay, so what will happen to our power, or what will happen to our I total? Okay, just that one. Anyone would like to answer? What if we have a reverse bias connection in this circuit? So what will happen to our answers, especially to our I total?
I think if it's a reverse bias, then we can still ignore the 0.7. It will be an open switch.
So
Then our I total should still be 0.08.
really, so we're going to have a current on the circuit. Seriously good.
I really don't understand. Well, I know that if it is a reverse bias, it will be an open switch, so there won't be current flowing. It will be an insulator.
Yeah. So it will actually work as an open switch, okay, or an open circuit. So in other words, we don't have a flow of current on this entire circuit. So your current will become zero, and then most of your answers right here will become zero, except for the R total, of course. So we still have a reading of 100 ohms, but the VR1, PR1, PRB, P diode, and then power across, or the PVS, will become zero. Okay. So with that, you already know that everything is pretty much ruined. Okay, if we have a uh, incorrect representation of diode in here. So you have to be careful when using a diode. Okay, so it will not repeat any current if it's in reverse bias. Okay, but anyway, so it's actually quite obvious anyway in the diode itself. So the black one is the positive one, and then the white one is the negative one, or the gray one. Okay. Okay, so we have the third approximation. So again, in third approximation, we now have to consider everything. Okay, so the threshold voltage, the belt resistance. So as a result, we have here still have the same current. Okay, so since we are now considering the threshold voltage in the second approximation, and then we still have the same R total, since as you guys uh, may remember, if the bulk resistance is less than 1 ohm, okay, then you can just ignore it, or you can just neglect it. So we have 0.75 in here. So it's like not having any resistance at all. So we still have 100 ohms. And then we have this value for VR1, PRB, and we still have the same result for the power across RB, even though we are now considering the bulk resistance. But yeah, so it will become 0 since we don't have resistance on this diode. Okay, and I think everything is the same. Yeah, everything is the same on our answer on the second and then the third approximation. So this will only change if we have 1.25 maybe or 1.5 bulk resistance. Okay. So again, I'll give you guys 20 seconds, maybe 20 to 40 seconds since everything is the same anyway. And then just give me thumbs up if everything is okay already on the third approximation.
Excuse me, sir. How do we calculate the total power in the circuit without adding up the values for PR1, PRB, and PD?
If it's a direct formula, then if it's P total, then you have to get the I total and then the V total. Okay.
Okay, so that will be P total over I total. That will give us. Do we use IV total? I mean, I total times V total to get the P total without adding the values of PR1, PRB, and PD?
Pardon? Do we need to use the V total minus?
I mean, if you want to get P total, do we have to use I total? That will be I squared total times R total to get our P total, right? I squared
Yeah,
have.
you're going to have the same result. Any of those formulas. So we can use I total or V total or I squared total times what is that one? Is it
R total.
yeah R total? Yeah.
Okay.
So those are just uh, different approach, but it will give you the same result. Okay. All right. So is there no other question? Okay. So it seems that there is no question anymore. So if ever that you have a clarification, so just ask me anytime. Okay. So let's now move on to the second example, which is the diode circuit problem in series and parallel circuit. So let's start with series connection first. So in here we have to solve the voltage output on the VO label, and then the total current K of the circuit, and then the total resistance, and then the total power of this circuit. So here is the solution. So this one is super simple. So V2 voltage output, okay, on this label. Okay, all you have to do is check, okay, the voltage that will remain or will retain after passing through this voltage threshold for this diodes right here. So 10 minus 0.7 is 9.3, and then minus 0.3 is 9 volts. So at this point, we have 9 volts on this VO or label VO. So that is why we have 9 volts in here. Okay. And then for the I total, so you have to use the V total divided by R total. So I total, V total is 9, okay, which is this one. And then the resistance is 3K milliamps. 3K only, okay, 3K ohms. And then the result is 3 milliamps. So just use your calculator to recheck whether this one is correct or no. And then for the R total, of course, it's 3K ohm. And then for the P total, you have to use the I total and then the V total, which is 10 volts. So 3 milliamps times 10 is equal to 0.03 watts. So again, please check everything. And then once everything is okay, so just give me thumbs up. Okay, great. So the point of this example is, so as you guys can see, our diodes is like working as a, another voltage source, but it's just have a different polarity wherein it's opposing the higher flow of current in here, or the higher voltage in here. So again, the rule in electric is whichever is the higher or the highest voltage source, that is the one that will dominate the entire circuit. So in here, we have 10 volts, but the other two is just 1 volt in total. Okay, so just deduct that one, and then we have 9 volts that is blowing on the entire circuit. Okay, so we'll stop here for now since we don't have enough time anymore. So we'll just continue the rest on the part 2. So goodbye for now, and then see you guys later.